do is I'll go through them, and then I will open up if anybody has any questions or wants to go over the particulars when it comes to action potentials. And I know that this last part is all physiology, so I'll leave time at the end of class for kind of a Q&A session. Okay. So, and again, as I said last week, a lot of this information is over content we've already covered in some shape, form, or fashion in the past. So now we're just pulling it all together and talking about it in the context specifically of a neuron talking to either another neuron and kind of focusing on a neuron talking to another neuron. So when we talk about this electrical gradient, right, versus a chemical gradient, I don't want to sound like a broken record, but just by way of reminder, these two concepts are tied together. The chemical gradient has to do with the difference in the concentrations for the ions that we talk about that are involved in the action potential on the outside, so in the extracellular fluid versus the inside of the cell. And for and the structures that establish those chemical concentration gradients are the pumps, in this case, the sodium potassium pumps. And those sodium potassium pumps pump 3 sodium out of the cell for every 2 potassium that they pump in. So they establish this gradient by which there is a much higher concentration of sodium outside the cell and the extracellular fluid than there is inside of the cell. And there is more potassium inside of the cell than there is outside of the cell. The other thing that the sodium potassium pumps do is they help to, they don't play as big a role in establishing, but they certainly help to maintain the electrical gradient, right? So the electrical gradient has to do with the difference in charge as measured in, so charge is going to be voltage as measured in millivolts. And again, comparing that from for the outside of the cell versus the inside of the cell. And the structure that is most, I suppose, relevant or important in establishing the electrical gradient and that gradient is one in which the inside of the cell, and when we talk about neurons, is much, much more negative than the outside of the cell. If you measure the voltage along the inside of the plasma membrane of a neuron, that voltage is negative 70 millivolts. So that's a much more negative charge than what you see on the outside of the cell. And the structure that is responsible for, the structures, I should say, that are responsible for establishing that gradient are the potassium leak channels, right? So we've talked a lot about leak channels versus chemically gated channels versus voltage gated channels. And leak channels are those channels that are embedded in the membrane that are always open. So they constantly let the ion that they are designed, if you will, to allow to pass, they continually let that ion move down its concentration gradient. So in the case of potassium, having neurons with all of these potassium leak channels in the membrane is going to allow potassium to constantly leak or continually leak out of the cell. And it's going to leak down its concentration gradient. So it's going to move from the inside of the cell to the outside of the cell. And potassium has a positive charge. So that's a positive charge leaving the cell. And it's those structures and it's that positive charge leaving the cell that brings the resting membrane potential of the neuron down to negative 70 millivolts, right? We oftentimes will talk about the membrane potential as the electrochemical gradient because that electrical gradient is dependent on the chemical gradient that's again established by the sodium potassium pumps. And then Ohm's law. So Ohm's law, if you've taken physics, you're probably familiar with Ohm's law, but what Ohm's law says is that current is proportional or equal to voltage divided by resistance, right? So what this tells you is that the greater the voltage gradient, right, the faster the current. And the current has to do with the movement of electrons. So the greater the difference there is, so and how that translates to this material is that the greater the gradient, so the more negative the resting potential, when those gates are open, the faster the current, the faster the ions will move down their concentration gradient. And then current is inversely proportional to resistance. And so as resistance, and resistance can be caused by a variety of different things, but if we're because we talked about the myelin sheath, right? So using this to describe what happens and why the myelin sheath makes the action potential move faster down the length of the axon. Without the myelin sheath, as I told you all last week, that action potential has to be generated at, how a bunch of, just think of it as many, many different places along the axon, right? That action potential has to move by opening and closing voltage gated channels. When myelin is there, the action potential jumps. So the action potential does not need to be generated in the areas where there's myelin. It just, those ions diffuse across that myelin sheath. And so having myelin present on the axon decreases resistance. And if you decrease resistance, you're going to increase current. You're going to increase the rate at which that action potential moves. Okay, so again, as far as neurons are concerned, I do want you to know that the resting membrane potential for a neuron is negative 70 millivolts. And I expect you to know why, right? I expect you to know what that chemical gradient is for the ions in question. So it's going to be the chemical gradient for sodium and potassium. I expect you to know the structure that establishes that chemical gradient. As I just mentioned, the sodium potassium pumps. I expect you to understand what the electrical gradient, what that means, and the structures that are responsible for establishing that electrical gradient. So again, the potassium leak channels, and then the sodium and potassium pumps, of course, also contribute a bit to that resting membrane potential, the difference in charge on the outside versus the inside of the cell, and they help to maintain that by, again, pumping 3 sodium ions out for every 2 potassium they pump in. So in that scenario, those pumps are pumping a positive charge. Sodium has a positive charge out. They're pumping more of a positive charge out of the cell than they are pumping a positive charge into the cell. Okay, so depolarization and hyperpolarization, right? These are the 2 events of the action potential. So I expect you to know what happens during these events, during an action potential, right? We're starting at negative 70 millivolts as the resting membrane potential. And then when an action potential is generated, and the action potential is generated when the threshold value is reached for a neuron, that threshold value is negative 55 millivolts. And so when that threshold value is reached, and we'll talk about excitatory and inhibitory postsynaptic potentials here in a moment, but which those are the potentials that ultimately get summed or added together in order to see, or I guess they get added together, and if that addition results in bringing the value from negative 70 to negative 55, then an action potential will be fired. So if an action potential does occur, what happens at negative 55 millivolts is that the voltage gated sodium and potassium channels open. But there are many, many more voltage gated sodium channels than there are potassium channels. And so when voltage gated sodium channels are open, sodium will rush into the cell because of the chemical gradient, and that will bring the value from negative 55 into the positive range, into, let's say, positive 30. That value, don't care that you know that particular value, but I do expect you to know that it brings it above, above 0, so into a positive direction. So that event of going from negative 55 to positive 30, that's depolarization. So depolarization is due to the opening of the sodium channels. And then what happens at that positive value, positive 30, I keep saying, is that the sodium channels the voltage gated sodium channels will close, and the voltage gated potassium channels remain open. And so based on that, potassium will leave the cell through the voltage gated potassium channels, and having that positive charge leave will drop the membrane potential back down to the resting membrane potential of negative 70. And then what also happens is you get the opening once you get during the repolarization event, which is the opening of the potassium channels, you also get the opening of chloride channels. And because of the concentration gradient for chloride, and that concentration gradient mirrors the concentration gradient for sodium. So you have much more chloride outside the cell than you do inside the cell. And so when those chloride channels are open, chloride will enter the cell. And so that's an additional negative charge entering the cell. And so that drops the value kind of transiently below the resting membrane potential. And so we go from -70 to -80, and that event is called hyperpolarization. So I expect you to know those different terms: depolarization, repolarization, and hyperpolarization, and the structures, the channels that are responsible for those events. Okay, so graded potentials. And again, this concept we've already actually talked about, but I don't know that I've used the expression graded potential. But graded potentials are local changes in the membrane potential that occur in the receptive area of the neuron, right? And the receptive area, the receptive segment, is made up of the dendrites and the cell body. Graded potentials can either cause, they can cause depolar. So we'll talk about the structures that are involved in graded potentials, but graded potentials can either be graded potentials that bring the membrane in a more negative direction. So they can be potentials that hyperpolarize the membrane, or they can be potentials that start to depolarize the membrane or bring that membrane potential in a more positive direction. And what determines whether or not the potentials are going to be hyperpolarizing potentials or depolarizing potentials is the neurotransmitter that binds to the specific receptor on the dendrites and therefore determines which channels are opened. When we talk about channels, and last week we talked about the types of chemically gated channels that we find in the receptive segment, but just by way of reminder, we have what we call chemically gated ion channels, cation channels, and those cation channels are going to allow either the passage of sodium or the passage of potassium, depending on the neurotransmitter that binds. And then we also have embedded in the receptive segment chloride receptors for chloride channels, chemically gated chloride channels. And so when chloride channels are open, again, chloride will enter the cell because of the chemical concentration gradient for chloride, and so that will hyperpolarize the membrane. And so as far as the neurotransmitters and the types of receptors that they bind to, or I should say, with regard to neurotransmitters and whether or not those neurotransmitters cause hyperpolarization or depolarization, that is totally dependent on the effect that that neurotransmitter has on that specific receptor. So that's not something that you need to know, but you do need to understand the concept of graded potentials when it comes to either causing depolarization or hyperpolarization. I think, is there anything else I want to say on this side? I think that's it. This the concept of the sub-threshold value. So sub-threshold value would be any value that is below the threshold value. And if we're below the threshold value, it's a value that's not going to be adequate for generating an action potential, right? So you can have graded, and we can and do have graded potentials that occur in a neuron that bring the value from -70 into a more positive direction. So you might, for example, have a little bit of neurotransmitter that is secreted into a synaptic cleft and binds to receptors. Let's say we're talking about a neurotransmitter that opens up sodium channels. So that neurotransmitter binds onto the receptors on the dendrites. It opens up sodium channels, but it just opens up a few. There's only a little bit of neurotransmitter in this scenario. And it opens up enough of those channels that sodium rushes in, and we go from a value of -70 to -60, right? That is not going to cause an action potential, because in order to generate an action potential, which is an all or nothing event, you have to reach -55. You have to, in the -55 is again the threshold value for a neuron. So you have to reach the threshold value in order to generate an action potential. Even if you depolarize, even if you have depolarizing graded potentials, if you don't reach -55, you will not get an action potential. Okay, so this is an illustration that we've already gone over, but just and I think I mentioned to you all last week, I think this material lends itself really well to diagrams, to drawing yourself little diagrams. And so when you are tested on this material, I would highly recommend that you draw little diagrams and you remind yourself of what you find in these areas of the neuron, right? So we're looking at a multipolar neuron right now, um, which of course would be a motor neuron. And so that neuron is going to have dendrites that come off of this cell body, and that's going to be where the receptive segment is. And so then you need to remind yourself, well, what do we find in the receptive segment? Well, we find chemically gated cation channels and we find chemically gated chloride channels, right? And they're chemically gated, and what that tells you is that what opens them is neurotransmitter, the binding of a neurotransmitter to its receptor. And then the initial segment, again, this is where, and one other thing I want to say about the receptive segment. So this is where, of course, the receptive segment, this is where the graded potentials are going to occur, right? It's going to be the opening of the various channels, various ion channels that cause the graded potentials. And then those graded potentials are added together, or there's a summative effect of those graded potentials that occurs in the axon hillock, which is the initial segment, right? So this is why last week we talked about the fact that action potentials are general. I said it's the axon hillock, or the initial segment, is kind of the trigger for the neuron. And that's because the action potential, if it's going to occur, is fired from the initial segment. This is where the graded segment or the graded potentials are added together. If, in fact, an action potential, if that threshold value is reached and an action potential is fired off by this neuron, then that action potential will be generated along the conductive segment. And so one other thing I want to say about the initial segment is, again, doesn't say it on this slide, but just remind yourself when you're drawing your little pictures of the structures that you find in each of these areas. So in the initial segment, this is where you're going to find voltage-gated sodium channels and voltage-gated potassium channels. And you're going to find voltage-gated sodium and potassium channels in along the rest of the neuron. So you find them in the initial segment. You also find them in the conductive segment. And then in the transmissive segment, this is where you're going to find the calcium pumps and the voltage-gated calcium channels. And so when that action potential gets down into the transmissive segment, it will open up the voltage-gated calcium channels, and calcium will move into the synaptic knobs, right, which are a portion of the transmissive segment. And they will move in that direction because of the concentration gradient for calcium that is established by the calcium pumps, which pump more calcium, which are continually pumping calcium out of the neuron. So there's a much greater concentration of calcium outside than there is outside of the cell than there is inside of the cell. Okay, so this is what I was mentioning a moment ago when I was talking about excitatory and inhibitory postsynaptic potentials. That's what EPSPs and IPSPs are. Those are acronyms, again, for excitatory. The P stands for post, the S for synaptic, and the P for potential. So excitatory postsynaptic potentials and inhibitory postsynaptic potentials. And whether or not, and what causes an excitatory postsynaptic potential is going to be the opening of a chemically gated sodium channel, right? And so again, if sodium channels are open because of the concentration gradient, sodium will enter the cell, and that will bring the value of the membrane potential in a more positive direction. So that's why we call them excitatory. And then inhibitory postsynaptic potentials are due to the opening either of the chemically gated potassium channels or the chemically gated chloride channels, because the opening of either of those channels are going to result in the movement of the resting membrane potential in a more negative direction, which will make it harder, if you will, to reach the threshold value that's required to generate an action potential. Also, as I mentioned, the specific neurotransmitter that cause either EPSPs or IPSPs. That's totally dependent. It's kind of a context dependent type of situation. So that's not something you need to know. It's dependent on yeah, the effect that that particular neurotransmitter has on that particular neuron, whether or not you're talking about a sensory or an afferent neuron versus a motor or an efferent neuron. Okay, and then another concept that's a part of this is that when we talk about EPSPs and IPSPs, those are generated often at the exact, or those are yeah, generated is the word I guess I'll use, at the exact same time, right? And that's because if you go back to this picture, right, and we were talking last week about how for one neuron, for what we call this neuron, by the way, that's where the neurotransmitter is binding to the receptive segment, we call it the postsynaptic neuron. The postsynaptic part, that tells you that this is the neuron that has neurotransmitter that is binding to the receptors. But this, and actually, hold on one moment, I want to make sure. I'm going to shut the door. So hopefully you guys don't hear that background noise. These EPSPs and IPSPs are being generated simultaneously because this one neuron is going to be synapsing oftentimes with many different presynaptic neurons, right? So you can have, let's say, 10 different presynaptic neurons whose synaptic terminals are synapsing with the dendrites for this one particular neuron. And so whether or not an action potential is generated is going to depend essentially on whether or not the EPSPs, whether or not there are more of those than there are IPSPs, right? Because if you add the inhibitory postsynaptic potentials with the excitatory postsynaptic potentials, the inhibitory potentials are going to essentially negate the effect of the excitatory postsynaptic potentials. Yeah, which is what this slide goes over here, right? So again, there's this summative event that occurs in the initial segment by which the excitatory and the inhibitory postsynaptic potentials are added together. And if you have more excitatory than inhibitory, and if you have enough excitatory that you reach the threshold value, then you will generate an action potential. And then also the reverse is true. If you either don't have enough of the excitatory potentials and or you have more inhibitory than you do excitatory and you are not able to reach that threshold value, then an action potential will not be generated. And then this concept of spatial versus temporal summation. These are two different ways in which graded potentials are generated, right? So you can have graded potentials that are generated and then summed together to reach the action potential happening either because of the situation I was just discussing by which you have many different pre-synaptic neurons synapsing with one postsynaptic neurons, or you can have, let's say, just a 1-to-1 ratio of pre and postsynaptic, but you can have that presynaptic neuron generating or releasing neurotransmitter very quickly in a short amount of time, right? So if that occurs, if you have a lot of those graded potentials that are generated in a short amount of time, those can be summed together. And if they're excitatory, then you can reach the threshold value. We call that temporal summation. So temporal meaning that you're summing graded potentials over time. And so if you get, again, if there's a lot of them occur within a short period of time, you can reach the threshold value and generate an action potential, or you can reach an action potential if you have a bunch of different presynaptic neurons that are firing off and that neurotransmitter happens to be excitatory for this neuron, and you add those together, and those will allow you to reach the threshold value. Okay, so I think I said everything I want to say on this slide. Again, action potentials are all or nothing. So if you reach that threshold value of -55, you will generate an action potential. If you don't reach that specific value, you will not. No matter what, again, it's kind of like firing off a gun. If you put enough pressure on that trigger, you're going to fire the bullet. It doesn't matter at that point, if how much pressure you're putting on the trigger, you just have to put enough pressure to ignite the gunpowder. And so it's the same, it's conceptually very similar to what we see with the neuron. If you have enough of those graded potentials to reach the threshold value, you will generate an action potential. That action potential moves at with the same velocity, no matter how, I guess, no matter how hard you pull on the trigger, right? No matter, as soon as you reach that threshold value, the action potential takes place. Okay, so let's see. I think I've said everything on this slide as well, um, as I am wont to do. I tend to kind of talk and talk and talk and don't time it out with my slides as well. But hopefully, that's good in the sense that now this is those are concepts we just talked about, and so as you're going through, hopefully all of this, the information on this slide makes sense, right? Do make sure that you understand what depolarization, what structures are responsible for causing depolarization of the plasma membrane, right? So again, it's going to be the opening of channels, um, the opening specifically of sodium channels, because that will cause the resting membrane potential to move from a more negative value to a less negative value. Um, and then for repolarization, as I already discussed, it's going to be due to the opening of the potassium channels, and then hyperpolarization is going to be potassium channels and chloride channels. Okay, so this is a clinical view that's presented in your textbook. Um, and it's one in which they do a little blurb on some of the different anesthetics that are, and one of those being lidocaine, or any of the canes, lidocaine being one of them. So lidocaine, what the way in which lidocaine causes, it's a local anesthetic, so it causes numbness in the area in which it is applied. And the way in which lidocaine works is that it essentially inhibits the voltage gated sodium channels. And so if you inhibit the ability of those voltage gated sodium channels, if you make it so that they can't open, you're not going to ever generate an action potential. And if you don't generate an action potential, you don't have a nerve signal, right? And if you've ever had any dental work, for example, done, you probably can appreciate just how effective blocking those voltage gated sodium channels from opening, how effective that is. Um, and how it really does cause, or I should say, how it really does make it so that you don't, that signal is not, there's no signal generated, no pain signal, which would be uh, a type of action or type of neuron firing off an action potential, how that's not something that occurs when lidocaine is causing its effect. And then, oh, and then ice, in case anybody's curious about how ice works, right? Most of us are familiar with the phenomenon by which if you ice an area, that helps to numb the area. And the way in which ice works is it doesn't stop the generation of the action potential, but it slows down. It slows down the transmission, slows down I should say, it makes it so that fewer neurons generate action potentials for those particular sensory neurons that are being iced. Okay. Um, and then again, repolarization, that's due to the opening of the potassium channels. And it's when those potassium channels are open, potassium will leave the cell, and that will bring the value back down toward the resting membrane potential. Um, the other thing that occurs during repolarization is that bringing that value back down into the range of -70 causes the voltage gated sodium channels to return back to their resting state. And then, as I mentioned, hyperpolarization is due to the fact that once we get down close to the resting membrane potential, that value opens up the voltage gated chloride channels. And then another phenomenon that plays a part in hyperpolarization is that the voltage gated potassium channels tend to stay open. So reaching the value of -70 doesn't cause an automatic closure of the voltage gated potassium channels. They tend to remain open just a tiny bit longer. Um, and or you can think of them as they're just a little bit slower to close. And anytime that they're open, potassium is going to continue to leave the cell. And so that's another thing that helps to, or that plays a role in the hyperpolarization event that we see um, in the neuron. And then another concept that I'm sure I have a slide going forward that covers it, but I'll just bring it up right now. The time during which an action potential is taking place, that's called the refractory period, right? And during the refractory period, during the absolute refractory period, you cannot generate another action potential. In order to generate an action potential, the cell has to be at least at its resting membrane potential. And in this case, with the neurons, it's -70. When during the hyperpolarization event, during that period of time, it is harder. That's what we call the relative refractory period. And we call it relative instead of absolute because you can generate another action potential during the relative refractory period, but it takes a pretty large stimulus to do so. And that's because we're in a more negative direction than the resting membrane potential. So it's going to take a greater stimulus to go from -80, for example, to -55 than it will from -70 to -55. Well, there you go. I figured I had a slide. So yeah, so absolute versus relative has to do during the absolute refractory period. You cannot generate another action potential. During the relative refractory period, you can. It's just going to take a greater stimulus than it would if you were to be starting at the resting membrane potential. Okay. So then the transmissive segment, what we see again is the action potential reaching the transmissive segment, and that action potential is going to open up the voltage gated calcium channels. And because of the chemical concentration gradient established by the calcium pumps, by which more calcium outside than it is inside of the cell, when those voltage gated calcium channels are open, calcium will enter the synaptic knob and it will coat those vesicles that have a negative charge along their plasma membrane. And it'll coat those vesicles because calcium is a positively charged ion. And so when calcium coats the vesicles, that coats them in a positive charge, that allows those vesicles to merge with the plasma membrane of the synaptic knob. We call the plasma membrane of the neuron the neurolemma. I'll just continue to say plasma membrane just for the purposes of visualization as we're going through this process. And also because I'm not drawing for you guys the way I would in a face-to-face scenario. So it allows the vesicles to merge with the plasma membrane of the neuron. And in doing so, those vesicles will undergo exocytosis and release their neurotransmitter into the synaptic cleft. Okay. So when we talk about the velocity of a nerve signal, we've already talked about how myelination is very important, right? The more myelinated an axon, the faster the velocity. When we compare myelinated axons to axons that are not myelinated axons have a much, much faster rate of conduction of the action potential along the length of the axon. And then another factor that plays a really important role in the velocity of the nerve signal is the diameter of the axon. So the larger the diameter, the faster the velocity. And then finally, continuous versus saltatory conduction. We've already discussed, but just by way of reminder, saltatory conduction is the kind of conduction that we see in myelinated axons, right? And this is, think of saltatory conduction as the action potential jumping from, we call these, if we're talking about an axon in the peripheral nervous system, we call these the nodes of Rambier, right? So in saltatory conduction, the action potential jumps from node to node, and therefore it only has to be generated where the nodes are found. And that's why it's such a faster type of conduction. With continuous conduction, which is the kind of conduction we see in unmyelinated axons, the action potential has to be generated along the length of the axon. So that takes more time because there's more resistance. And that's why saltatory conduction is much faster than continuous. And then when it comes to nerve fibers, so we group nerve fibers into 3 major groups. So group A is going to have the fastest type of, or the fastest velocity of nerve signal conduction. And the reason it's going to be have the fastest velocities because these are axons that have relatively large, that are relatively large in diameter, and they tend to also be relatively heavily myelinated, right? So examples of group A fibers are going to be somatic motor neurons, right? The motor neurons that are responsible for skeletal muscle movement. And then also the neurons that are responsible, the sensory neurons, neurons that are responsible for taking information from those structures under conscious control, like skeletal muscle, back to the central nervous system for processing. And then group B and C, group B is kind of mid-range with regard to velocity, and group C includes those fibers that have the slowest rate of conduction. But group B and group C fibers are going to be slower because they have smaller diameters. In some cases, they might have the same size diameter as the group A, but they're unmyelinated, or we see with a lot of group C fibers, these fibers are going to be both relatively small in diameter and also unmyelinated. And examples of the slower types of fibers are going to be, for example, some of the visceral motor neurons. So those motor neurons that are responsible for smooth muscle control, and then also the sensory visceral neurons. Oh, and one other thing I want to say, I don't expect you to know the exact values. I just want you to know that group A is the fastest, followed by group B, and then group C. Okay, so we have different types of neurotransmitters, right? We group neurotransmitters into these various groups depending on their chemical composition, right? So we can have, for example, one group are going to be the amino acids. So glutamate, glycine, all of those amino acids can and do act as neurotransmitters. Acetylcholine is its own group. So acetylcholine, we've talked about acetylcholine mostly in the context of the neuromuscular junction. And when it comes to the effect that acetylcholine has on somatic motor neurons, acetylcholine is excitatory, right? We've seen that. It opens up the chemically gated sodium channels, and sodium will enter the cell, and that's an excitatory type of event. Acetylcholine is not always excitatory. There are situations in which acetylcholine can be inhibitory. I don't expect you to know those specific difference or the specific scenarios in which acetylcholine is inhibitory, but I do expect you to know that acetylcholine can be both excitatory or inhibitory depending on the situation. The monoamines, so the monoamines are a subgroup that includes what we call the catecholamines, and the catecholamines, examples of catecholamines are dopamine, norepinephrine, epinephrine. The catecholamines tend to be excitatory, but again, it's not a hard and fast rule. And then finally, we have what we call the neuropeptides, which are chains of amino acids. And an example of that would be somatostatin. So those, and then this table right here shows you, kind of visually shows you what those different groups look like when it comes to their molecular makeup. Okay, so when it comes to modulation or controlling the effects of neurotransmitters, right? We've already talked about how neurotransmitters can, and it's very important that they, after they have caused their effect, that they are removed from the synaptic cleft, and how that is accomplished by, one way I should say in which it's accomplished is by the degradation of the neurotransmitters by the specific enzymes that we have that are responsible for breaking those neurotransmitters down. So we talked, when we were talking about the neuromuscular junction, about acetylcholinesterase, which is the enzyme that breaks down acetylcholine. Another way in which the neurotransmitter is removed from the synaptic cleft is by reuptake. So that if that neurotransmitter is not broken down by the enzyme, it can and will bind to receptors on the synaptic knob, and the binding of that neurotransmitter to those receptors will cause the synaptic knob to undergo endocytosis and to pull that neurotransmitter back in to the cell, and then that neurotransmitter is essentially broken down and recycled by the cell. Um, so for this slide, the differences between facilitation and inhibition. So facilitation can happen, facilitation meaning the facilitation of the effect of the neurotransmitter on the neuron. So it can happen when, because either there's a lot or more, we shall say, neurotransmitter in the synaptic cleft than what is normally found, or it can happen because the number of receptors on the postsynaptic neuron in the receptive segment, that expression is increased. Either of those events would help facilitate the effect of a neurotransmitter on the postsynaptic neuron. And then inhibition is another kind of modulatory event that occurs in the neuron, and that occurs basically, when the opposite events from facilitation happen. So when either the number of receptors is downregulated and or less of a neurotransmitter is secreted into the synaptic cleft. Okay, and then finally, when we talk about the way in which neurons communicate with each other, we describe those interactions as what we call pools, right, or neuronal circuits. So we have four basic types of circuits: converging, diverging, reverberating, and then what we call parallel after discharge. And the difference between them essentially is in the way in which they're arranged and then the number of synapses that are taking place. So with a converging circuit, you have many different presynaptic neurons that are synapsing with one postsynaptic neuron. With a diverging circuit, you have usually the same or a similar number of presynaptic neurons that are synapsing with several postsynaptic neurons, right? So if you have four, in this case, you have four presynaptic neurons that are synapsing with five postsynaptic neurons. With a reverberating circuit, the reverberating circuit in parallel after discharge, this has to do with the arrangement. So with the reverberating circuit, the neurons are arranged into a circuit. These are the types of circuits that you see that control a lot of, I guess, reflexive types of events. So for example, breathing, right? Breathing is not under conscious control. I mean that we can change our patterns of breathing, but we have what we call quiet inspiration and quiet expiration that occurs reflexively, or automatically, and that is made possible by this reverberating circuit. And then parallel after discharge, this is a type of arrangement we see of neurons that are involved with higher levels of thinking. So a lot of the circuits that you find that within the frontal lobe, or I suppose just within the cerebral cortex in general, are parallel after discharge circuits. So it's kind of a complex type of arrangement of neurons.